look at the conformations of rings now. So rings are a little bit trickier, but we'll make our way through them. So a couple things first. They have the general formula C and H2N. So they're missing two H's so that we can kind of connect the ends together to make a ring. Now there's strain in these molecules, and it arises from two main areas. One is called torsional strain. Torsional strain, it is the repulsion caused by the electrons and between different groups when they pass by each other or when rotating a molecule around a single bond. And the other type of strain is called angle strain. That's strain caused when the actual bond angles in the atoms of the molecule differ from the ideal bond angles of their geometry. So there's a neat experiment that you can do that I wanted to highlight and show you here. So we can look at heat of combustion here. So the heat of combustion, it's the amount of heat that's released when a compound is burned with an excess of oxygen in a sealed container. And if you go on and take physical chemistry, or in some G-Chem classes you might have done something like this, but you might have done a calorimetry experiment. And in P-Chem you might have actually ignited it, or you might ignite it in something called a bomb calorimeter. If the compound has extra energy as a result of ring strain, that extra energy is released during that combustion. Right? So what we look at is a change in temperature by the surrounding water bath, right? And then we do some calculations to calculate our energy. So what we have here is a cycloalkane, CH2N for us. And we're going to add excess oxygen on there. We're going to get CO2 and we're going to get H2O. And then we get this heat of combustion, some energy. So there's a release of energy. So what we're going to do is we're going to look at this table and we're going to kind of talk about some energies here. So our reference long chain here, what you end up doing is you just kind of blow up different size or different length molecules, and then you figure out the delta H, and then you divide this by the number of carbons, and this will give you the heat of combustion per CH2. So this is our reference here, because linear molecules are not going to have any ring strain because they're linear, right? There's no ring that's formed there. So if we look at our trend here, cyclopropane has a delta H, a molar heat of combustion of 2091. Okay, you go up and you put cyclobutane in there. That's larger. That makes sense. There's more carbons. Cyclopentanes, they just keep going up, right? So as you go from cycloprop up to cyclooct, the numbers get larger, which is to be expected because you have more carbons there. But if we really want to get a value, a real picture, what we have to do is we have to weight that number by the total number of carbons in that molecule. So we're going to take 2091, we divide it by 3, and we're going to get 697. So if we take this and divide it by 4, then we get this, right, divided by 5, so on and so forth. So we're weighing these by the number of carbons that are in that ring. Now, we can then figure out the ring strain per CH2 group, because we can take the number here, which is our heat of combustion per CH2, and we can pull out, right, the molar heat of combustion for a CH2 group in which there is no ring strain. And what we're left with is our ring strain per CH2. So here's where things get kind of interesting. We'll start off with 39 for cyclopropane. Falls down to 28, so it's getting smaller. Down here with cyclopent, it's 6, right? And then cyclohex gives us 0. So cyclohexane is special. It has a ring strain per CH2 that's similar, or in fact almost identical, right, in this case, to our long chain alkane. And then hep a little bit larger, and oct a little bit larger than that, right? So a little bit of a jump there. Now, if we wanted to determine the total ring strain, we could take this number and we would multiply by the number of carbons. Right? So times 3 gives us 117. And then here we can see the total ring strain, again, for cyclohex is 0. And that's the magic thing that we need to remember. Cyclohexane is special. So let's look a little bit closer here at some of the strains that we see in the lower number cycloalkanes. So cyclopropane is 1, 2, 3 carbons, right? So we know that each of these atoms are sp3 hybridized, and we know the desired bond angle is 109 degrees. But in this triangle, technically, the bond angle is 60 degrees. So the strain here is 109 minus 60 degrees. Right, so you get 49 here. Now it's not perfectly 49, but there is angle strain there. So part of the reason why it's not 49 is because we actually get a little bit of a bend here. So if you look at this, it's a little bit of a bend in the overlap of the sp3 orbitals. Okay, so that helps accommodate that ridiculous amount of angle strain. The other thing that we see here is that the molecule has torsional strain because all of the atoms are eclipsed. So the H atoms, if we look at this front carbon and this back carbon, these H atoms here are eclipsed with each other, right? Here's your front atom here. This one goes behind here. And there's very little twisting that we can do with this molecule to alleviate that type of strain. Now if we come down here below and look at cyclobute, right, here's our 4 carbon ring, bond angle of 90, and remember we're still sp3 or 109, so we still have angle strain here of about 19 degrees. So if we look at just a totally flat molecule of cyclobutane, we can see that the H atoms are actually right on top of each other perfectly, so they're eclipsed too. But this molecule can actually do something interesting. So this is not the actual structure of cyclobutane. Instead, what cyclobutane does is it kind of twists itself. And when it does so, you end up getting these H atoms here that are kind of, so they're not staggered, but they're not quite eclipsed on top of each other anymore. So it has a little bit more of a wiggle room to do that type of twisting. Now when we get down to cyclopentane, here we have enough twisting capability that we have H's along those carbons that actually are staggered with each other. So you can see this is the planar form of cyclopentane. If you took it over and rotated it on its side though, if it really adopted this conformation, you could see that down these carbon-carbon bonds right here, that these H's are eclipsed, right? And if we rotated this around, we end up seeing eclipsed on every single atom, right? So all those H's would be eclipsed. Now, when you do that twist, you end up getting this conformation. So we can see that we have a bend here, right? So we're taking one end of the carbon cyclopentane ring and we're bending it, right, and giving it that twist. You can see we are a little twisted here. And what we get is we get H's that become slightly staggered here. So as we move around, we're no longer eclipsed, right? And now there's still ring strain in this because you end up having some angle strain because you're not able to adapt a perfectly 109 bond angle there. So it's close to 109.5, and that's why we have very little angle strain there. Now, it's cyclohexes, the special one. Cyclohexane has no angle strain and no torsional strain. Remember, it was essentially equivalent per CH2 molar heat of combustion to that of our reference linear long chain alkane.